Yeah, so good morning. Welcome back to the lectures on the EFT method to post-Newtonian gravity. Yeah, I was just writing down again where we left off yesterday. So we were discussing how to do the path integral over the orbital modes of the gravitational field of the metric, HO. And for that purpose, I mean, it can be convenient to rescale actually the field degrees of freedom such that there's no scaling with the relevant constants in the propagates. I mean, that's a choice. One doesn't have to do it. But then if one does so, one just has to look at the vertices in the Feynman diagrams to figure out the order at which one is working or at which the Feynman diagram will enter. So for that, well, one needs to analyze what exactly is the prefactor in the quadratic part in the fields, because that is what gives you the propagator. And it goes like this. And since it's quadratic, one has to rescale with the square root of the inverse of that. So then in the quadratic part of the field, there's no prefactor of G and H bar, etc. So that's basically the logic. But then basically in each of the vertices for each line, so to say, or for each power in the field, one gets this extra factor. So this is what led us then to these kind of scaling rules, if you want. So for a field vertex, for each graviton line, you get exactly this factor, but there's the overall factor in front of the whole action going like this. So this is why there's a -2 here, not just the power to the n. But for the word line, basically, one just gets for each graviton line, one gets exactly this power, and the overall 1 over h bar, which is coming from here, right? So it's in front of the whole thing. So that's the rules that we have. Now, it's also important to notice that the word lines currently are just external sources, right? So there's nothing propagating here. The logic is more that we integrate out the field, and then we get an effective action which we could vary and then get equations of motion for the word lines, right? But we are not integrating out the word lines or integrating out their degrees of freedom, right? We treat them as external sources. So the word lines here are external sources. Which means there are no propagators. Yeah, I mean, one doesn't have to do it like that. So there's one approach, for example, which we call word line quantum field theory, where we actually also integrated out the word line degrees of freedom, but more in the context of scattering, where it's a bit easier, so to say, because you start with a straight line and then that straight line slightly gets perturbed in the scattering process. While here, I mean, if you already start with bound orbits, this is a little more complicated, so to say, at least if one wants to do it with QFT methods. So this maybe still needs to be worked out. But here, yeah, the approach is very simple. We just don't integrate out the word line degrees of freedom, and this works quite well to very high post-Newtonian order. Now, what we'll start with now is first looking at what people call the so-called diagram topologies. So what that means is basically that in this process of post-Newtonian approximation, we will see that we have to split the metric into 3+1 pieces, so into time components and space components. This is basically because we want to track all the factors in 1 over the speed of light properly. So we basically have to do that. But this means that we not only have one gravitational field propagating and one propagator, but we have one for every component in this decomposition. So we have the spatial part of the metric, the time-time component, and the time-space part, which will get separate propagators. Now, what topologies here mean is that we draw the diagrams, but we don't care which of those components of a metric we mean by the propagator, right? Because at this point, we just want to figure out what is the scaling in G in the gravitational constant. Because also those vertices will be augmented by further powers in the speed of light coming from time derivatives, for example, in the field action, or also from velocity terms in the wordline action. So at this point, what topologies means is we get just the scaling in the gravitational constant. But also we want to figure out at which order in H bar the diagrams contribute, because we are interested in the classical contribution mainly. So we want to get rid of the quantum pieces. Now, what is the classical part actually? Well, it's not the H bar to the 0 part. So that's maybe a little unintuitive at first, but it's the 1 over H bar part. And this is because when we integrate out some fields using the path integral, we want to rewrite the result again as e to the power I divided by H bar times the effective action. So the leading order piece basically always goes like H bar coming from this factor here. And then at this point, one could take the classical limit, which means one basically can look at the place where the phase, the exponent is stationary. And this gives you the classical path for the word lines, right? But there's always this 1 over H bar in front. So the classical part, we indeed identify by the 1 over H bar piece, which naively diverges, but also it has to be because basically the exponent has to become large, right? So one is in the regime where one can apply the stationary phase approximation. Now, physically, what this means is, well, since H bar is not a dimensionless quantity, physically, we want that H bar divided by the angular momentum is much smaller than 1, right? Or in other words, we are looking at orbits with a very large macroscopic angular momentum. Yeah. So here L is the angular momentum. All right. So let's start. Let's see where we get. So the simplest case would be 0 Pn. Now we cannot count powers in 1 over c yet, but as we've seen last time, the epsilon parameter is like this. So at least if we go to some order in the post-Newtonian expansion, we know the maximum power in G that is allowed at that order, right? We may not get all the contributions of V square over C square, but we definitely have to include all the diagrams with a certain G scaling. And at 0 Pn, this means we want to go to linear order in the gravitational coupling. So here we want all diagrams of order G and H bar to the -1, following those rules here. Now, also, we want to have binary system, so we definitely need to have 2 word lines, right? And now the easiest thing would be to connect them with one propagator, right? So like this. And now if we look at our counting rules, this gives us basically 2 times this guy with a power of 1, which, well, the h bar scaling is 1 over square root of h bar squared, because we have 2 vertices. So it indeed is 1 over h bar. That works. And the g scaling, so it's square root of g squared. Sorry, not squared, but square root of g. But then we have 2 vertices, so we have to square it. 1 square root of g from here and 1 from here. So that's also linear in g. So that indeed scales in the way we want it to. Now, we also see that we cannot really add any field vertices here, because that gives us further powers of g, right? So we are basically left with 2 wordline vertices and 1 propagator that we can use. So other possibilities are only the following. We could have 2 vertices on the same wordline, going like this. Now, this actually is a self-interaction of the body with itself, right? So the point mass creates a field and it interacts with the point mass itself. That's badly divergent usually. So we'll see later what to do with that. And likewise, we can have it the other way around, like this. So then the second body is interacting with itself. And let me just mention for illustration purposes, how would the first quantum correction look like? Well, this would be the following, where you again take the 2 word lines, but now you take a vertex with 2 lines going out, right? So this gives you also a linear and g scaling, obviously. But the problem is then you have to connect things like this, right? Yeah, this gives you 1 over h bar, but then an h bar square from here. So that's linear, or no, that doesn't have any scaling in h bar. So this is order g and h bar to 0. And since the classical part is 1 over h bar, this is, so to say, already the first quantum correction. Okay, so this we want to drop. Now let's move on to the 1pn order. So yeah. Yes. Yeah. Yeah. So there is always an overall factor in front of the whole action. And for the word line, for the point particle part, it's 1 over h bar. And for the field part, it's this. So one has to take this factor for each graviton line and then multiply it by either this or that. Sorry. Yeah, exactly. Yeah, it's here. Yeah, it's here. 1 over h bar. Right? So this is basically where it's here. So this is the -2 here, right? So the square root of h bar to the -2 is 1 over h bar. Okay. Yes. Yes, it's here. Yes. Yeah. It is kind of hidden because you have the power to -2 here, right? So if you drop the power to -2, right? So you have the same exponent here, then you have right, you have h bar divided by g c square, right? So here's this extra factor, to the power 4, yes. Right? So this is the overall factor of the action that also goes there. Yes. Yeah. Right. Other questions at this point? Yeah.
It can
Yeah.
Could you tell why it is like
Why? Why this not? Well, I mean, I'm not sure how to explain it, right? I mean, it follows from the math in a sense. Yeah, but I mean, in some sense, this is a proper quantum loop, so to say, a proper quantum loop correction. While here, I mean, there's no, since there's no propagation along the world line, this is not really a quantum loop, right? This is just an interaction of the external source with itself. And it's also a completely classical thing that you would get also in a classical calculation with a point mass, yeah. Yeah, indeed. Yeah. So since we don't have propagation along the word line, yeah, I mean it's like a tree diagram. Yes. Yeah. Although one has to be a bit careful because some diagrams that I'm going to show now, which by the same logic would be tree diagrams, actually lead to loop integrals, right? So I mean, the intuition from particle physics doesn't always 100% apply here. Yeah. So yeah, actually that gets me to the first example, which will be would be a proper loop integral. But by this logic, it would also be considered as a tree diagram. So again, we have to write the two word lines here. And now let's, so to say, slightly modify this diagram over here because we know already it's scaling like power of g, right? So what can we do? Well, we could substitute one of the word line vertices by a higher point vertex, or we could try to insert a field vertex here, right? So let's try the first. Let's put a field vertex here. Now we could connect the other leg either here or up here, right? So let's do the first thing like this. And then in the end, I mean, we'll see that many of those diagrams, which are not 100% symmetric and the exchange of 41 and 2, I mean, you always have to write the other diagram with the two word lines flipped. So I will not do this explicitly now here. I mean, I did it here, but it's kind of obvious, right? So you have this diagram, but then you also have to flip the 1 and the 2 and add that as well. So anyway, yeah. Yes, okay. Yes. So this is g squared and h bar to the -1 again. So yeah, let's check if this works. So this was scaling fine. Now we add a vertex here. This with 3 legs. So this gives us h bar times g to the power of 3/2. But we are also adding another word line vertex down here, which is a 1 over h bar. So, okay, maybe let's write it down quickly. So we have h bar times g to the power of 3/2 from the field vertex. And then we have this guy here, which is square root of g divided by square root of h bar. No, is it right? Wait, okay, now I'm confusing myself. So yeah, okay, so here's the n-2. So that means, okay, this is just square root, right? All right, so this means the h bar cancels from the additional vertices that we are adding, and we get another power of g, right? So this is all right. This is exactly at this order. Now, another thing we can do, instead of modifying or adding a field vertex is we can swap a world line vertex against one with two gravitons going out. So let's do this. Now, basically, this means we are increasing here the power from n to 1, from n equal to 1 to 2. So we get a factor of square root h bar times g. But we are also adding another world line vertex with n equal to 1, which gives a factor of square root g divided by square root h bar, right? So again, the square root h bar cancels, and we get a square root g square, which gives another factor of g. So this also works perfectly fine. Then we have two more diagrams, which again will turn out to be divergent self-interactions, which is if we take this one, but we connect this graviton back to the same world line. So that's kind of a different kind of self-interaction. But again, this world line is interacting with itself. And even worse, if you want, we could connect this vertex twice with its own world line, right? So then we end up here. And then we have to flip all those diagrams, so exchange the 1 and 2 on the world lines, right? So that's all we can do. Now, I don't know if people here recall how to get to the symmetry factors of diagrams, more or less. I mean, it's not so important here for this lecture, but I mean, if one wants to do the calculations, then at some point one has to figure out those symmetry factors. So I will give them here later on, so you can do the exercises, all right. But maybe if you don't recall, you could at some point look it up in the quantum field theory textbook. So this guy here, actually, since you, so to say, since this vertex connects 2 times to the same world line, it would have a symmetry of 2. So you would have to multiply a symmetry factor of 1/2 to the diagram. The same is true for this guy. This one is fine because the 2 lines go to different world lines, so to say, so it has no symmetry and therefore no symmetry factor. While this guy again has a symmetry factor of 1/2, right? Because from this vertex, both gravitons go back to the same world line, right? Now, for completeness, let me also just mention the quantum diagrams at order g square. Yeah. Exactly. Yeah. So at 1 p.m. we would have all those stuff. Although, I mean, as we'll see, we can quite quickly drop this guy and this guy and this guy and this guy. So more or less, it's those 3 topologies which remain at 1 p.m. And then we'll see. There will be more simplifications even. Yeah. Yeah, exactly. Yeah. So we have here g to the power 1, and here we have the g square diagrams. At most g square. Exactly. Yeah. So first order in epsilon would be linear in g square. Epsilon square, which is the first post-Newtonian order, is g square. Yeah. So this is basically, this is order epsilon, and this is order epsilon square. Yeah. Yes? Ah, yeah, okay. Yeah, that's a good point. Yeah, that's also very good. Yes, that's also possible. Yeah. Right. Yeah. Thank you. Okay. Other questions? Okay. So then let me mention some quantum diagrams at this order, just for completeness. Whoops. So I think one of them that I saw was this one here, where basically you take the first diagram, but then connect the two gravitons to the same vertex. So that's very similar to this guy here, right? And the other one at this order would be where one takes two worldline vertices with two gravitons going out and connects them like this. There might be more. I guess you could also move this vertex over here and this vertex over here and things like that. But I think you know how this goes, so to say. Right. Does anyone see further quantum diagrams? Yeah. I mean, it's also not so important for this calculation, but yeah. Good. All right. So now the next thing that we have to do is basically getting the Feynman rules in a more explicit form, so that we can also see more precisely the scaling of each term in 1 over the speed of light. And for that purpose, we have to do a 3+1 decomposition. I mean, one reason being that, so to say, the zeros coordinate, I mean, it's c times the time, right? So we have to kind of isolate all those factors of c properly in order to count them. So we have to split into time and space. And for that purpose, there's a form of the line element that is shown to be quite useful. So the line element, let me write it in terms of the proper time. Yeah, I'm going to use some mostly minus signature. So if I relate it to the metric, I get a plus here. Right, so in the mostly plus signature, you would have a minus here. But the form of the line element is basically invariant if you write it like this. So it doesn't depend on the signature really. Now we are going to write it in a form that has first been proposed by Kaluza and Klein in the context of so to say higher dimensional gravity theories, where they started with a 5-dimensional gravity theory, but then basically showed that you can, with a certain form of the line element, you can decompose the metric in a way that, so to say, you get a dilaton field and an electromagnetic potential and a 3-dimensional gravity theory, if you assume that there's no explicit dependence on the 5th dimension, basically. Now here, we will use the same decomposition, but in 4-dimensional gravity. And the reason why this works well, in some sense, is that to leading order, since yeah, we have those factors of c here, basically the interaction is almost instantaneous. So it's kind of at first approximation, there's little dependence on the time dimension. So this is why this decomposition also works quite well. And then we get kind of a gravitoelectric scalar field, a gravitomagnetic vector field, and then a 3-dimensional tensor field in this decomposition, which all entered different post-Newtonian orders. So it's a nice way to organize the decomposition and the expansion. So in the exponent, usually in the Kaluza-Klein decomposition, there's a dilaton field, but now here we put a phi, which basically is a Newtonian potential, like this. So this is in the dt square part of the metric. Then we have a vector potential. So here it's a three-dimensional vector potential. And you could call this the gravitomagnetic field. And so these square root scalings come from our rescaling over there. It's a bit inconvenient, but with this choice, it's like that. So this is how it looks like, the first piece. So we have a gravitoelectric potential, the Newtonian potential, and the vector potential for the gravitomagnetic field. And then we have the spatial part. So this is a similar exponent with a minus here in front. And then we have the flat spatial metric, delta ij plus square root of 4 times square root of 2 pi g divided by d square times a new field, which I'll call sigma here, times dxi dxj. And here I, j, k run only over the spatial dimensions. So it looks like this. And so we have kind of introduced the post-Newtonian fields, if you want, which are phi, the Newtonian potential, ai, the gravitomagnetic vector potential, and so to say the rest, the three-dimensional tensor field. And yeah, so this is inspired by the Kaluza-Klein decomposition. Now, another thing that we'll do now from now on is the following. We'll drop the factors I divided by h bar. Because basically they cancel in the classical action anyway. Right? In the sense that, I mean, we have made sure here that the diagrams all scale with h bar to the power -1. However, in the end, we'll put it in front of the action, right? And the classical action will be whatever comes out of the diagram calculation with I divided by h bar pulled out in front. And the factors of I, they always come, they always go with the h bar, right? So always when you have an h bar, it's divided by I, so they always go together. So if we take, in the end, the classical limit, for sure, all the h bar and I factors will go away. So we can just ignore them instead of carrying them around in the propagators and the vertices and so on. And yeah, right. Although, I mean, one could, of course, keep them if one wants to have a check that one did the algebra correctly. But yeah. Yes. Yeah. Yeah, you mean like adding? Yeah, but I mean, yeah, that's a bit tricky, so to say. Naively, I mean, it just gives, since it's the same diagram, it just gives the same factor, right? So it would be g square h bar to the -2. So you, in some sense, it would be subleading. It would be even stronger than the classical result. I think I maybe forgot to mention something. So we should only take the connected diagrams here, right? That's because, I mean, we are computing the full result, but then in the end, we have to rewrite the answer again as e to the I divided by h bar times the effective action. And in this Feynman diagram language, basically taking the logarithm of the result or writing the result as an exponent means you only take the connected diagrams, right? So this should be proven at some point in some quantum field theory lecture. Now, this diagram, since basically there's no propagation along the word line, means it's basically a disconnected diagram. So this diagram actually is, let me write it over here. So this diagram, since there's no propagation along the word line, is actually this diagram square. So it's part of the exponentiation. When you exponentiate this diagram, plus all the rest, basically you get this one as a second piece of the exponential, right? So this is basically, it's 1 plus this diagram plus this diagram square, 1/2, right? And so this is exactly this guy. So, I mean, you're right, it's there formally, but yeah, we drop all the disconnected diagrams. So, yeah. Okay, very good. Are there more questions? All right. So then, yes. Now, the next thing would be we have to obtain explicit expressions for the propagators and those vertices, and then, so to say, we can use those to assemble the actual integrals that are behind the diagrams, right? Yeah. Yeah. Uh-huh. I mean, naively, I would say, since I just moved this wordline vertex over here, the scaling has to be exactly the same as this one, right? This one? Yeah, so this is with n equal to 3. So you have 3 minus 2. So this gives one factor of this. And it's one word line, but we have 3 vertices with n equal to 1. So you have to set n equal to 1, but then you have this whole thing to the power of 3. Yeah. So yeah, so this applies for each vertex. That you add. Yes. Yeah. Okay. More questions on this? Okay. So let me then show you how this decomposition looks like when you insert it into the Einstein-Hilbert action. And we also have to use a gauge fixing. So here, I mean, we basically use a Lorentz gauge, or well, the standard gauge, let's say. And in principle, we should also do everything here in d+1 dimensions, so in generic dimensions. It's just that for the calculation later, this is not so important because there are no proper divergences that have to be removed. But at higher orders, so to say, one would have to do all of this in generic dimensions, so one can properly apply dimensional regularization. But here, I'm just going to write it down in 3 dimensions for simplicity. Anyway, if we now plug this into the Einstein-Hilbert action and the gauge fixing, and we take into account the rescalings that we did, which already simplify the quadratic piece of the action, then we get the following. So we get an integral over time and space. And the first quadratic term in the action is just, so to say, for the phi field with the Laplacian, so with 2 derivatives there, that's all. There are also 2 time derivatives, but they will come at higher orders due to our counting in 1 over c square. So they will come in a minute. But anyway, here we have a nicely normalized quadratic piece, which will give us propagators. We have a similar term for the gravitomagnetic potential. Just the sign is different. And yeah, I mean, it's a little difficult or weird maybe to absorb it in the normalization of A, because then you have to introduce factors of I. So this we have to keep like it is. And now we have the sigma fields where the propagator looks a little more complicated. So there we have some combination of deltas, which I'm going to write down in a second. But then again, the Laplacian and the other fields. So those are the terms that give us propagators. And this guy over here, it's delta I j delta k l minus, so this is for symmetrization, those brackets, minus delta I j delta k l. Yeah, so yeah, that's basically coming from the tensor structure and the constructions between those 2 sigmas. Yeah. Wait. No. This is not quite right. So P I J K L is this guy, but here we have the inverse. So this is not quite the trace reversal operator, so it's not equal to its inverse. But yeah, I mean, one can work it out still quite straightforwardly. But this guy then will appear in the propagator, right? Because the propagator kind of is the inverse of whatever is here between the fields. Okay, so those will give us the propagators. And now as the second line, which will give us vertices. So one vertex, so to say, is now coming from the second time derivative. Now these 2 would just combine into the wave operator, right? And if you would do a normal quantum field theory, you would get a propagator for time and spatial parts, so to say. But here, since we want to expand in 1 over c square, we get something a little unusual, which is a vertex with only 2 lines, right? And it contains basically 2 time derivatives. So that's a bit unusual in the Post-Newtonian approximation. And then we get the same thing for the A field. and another one for the sigma field. So those are two vertices. And then basically there would come three vertices and higher ones. Now, actually, what happens here is if you work out the vertices, you will find that they will all be higher order in 1 over c squared, fortunately. So that's also kind of thanks to this decomposition. So if one works in a different gauge or doesn't use this nice decomposition, you may have to take into account three vertices. But here, it's not the case. In particular, since the three vertex for the phi field, it kind of accidentally or because of the good choices contains time derivatives. So then it gets pushed to higher orders in the PN approximation. And that's nice because that means we can also, in the end, drop this diagram with the three vertex, right? Because when counting powers of G, it nicely would contribute. But then if we look at the actual vertex, it's higher orders in 1 over the speed of light. Yeah. Which, where, here or here? Here? Oh, yes, yes. Yeah. There's the dt square missing. Yeah, thank you. Yes, very good. Yep. Okay. So from there, now we can determine the propagators. And also we can write down Feynman rules for these two vertices. And then, so to say, after that, we'll have to look also at the point particle part and the point particle vertices. Okay, so first the propagators. Yeah, so the action is already normalized in a quite convenient way. So the propagators, in a sense, are rather standard. So for the phi field, so this would be a two-point function between two phi fields. Let me write it like this. So it is not so uncommon to partly work in X space and not completely go to Fourier domain because the word lines still have a position in them, right? So unlike in particle physics, where the external lines, so to say, can be taken as plane waves, and it's very natural to completely work in Fourier domain, it's not quite true here because the external sources, the word lines, are still localized on some position, right? So that's why it's sometimes useful to still write it down in X space. But then the actual integrals are usually done in the Fourier domain, right? So now let me write down the Feynman rule that follows from it. So we do have a three-dimensional Laplacian. So we do get basically an integral, a three-dimensional one, e to the k x1 minus x2 divided by k square, right? So if the Laplacian is two spatial derivatives, and in Fourier domain, this gives a factor of k each, so k square. And the propagator always is the inverse of what appears in the action here at quadratic level, right? That's kind of because in the path integral, the quadratic pieces give you a Gaussian integral, and if you work out a Gaussian integral with external sources, the result basically contains the inverse matrix of the matrix that appears here, kind of, right? So you need the inverse operator from here, and this gives you the propagator. However, now we also have the time dependence, but there's nothing happening there, so we can just write a delta function there. So for the time dependence, we just have a delta T1 minus T2. And that just represents the fact, so to say, that in the Newtonian limit, the field propagates instantaneously, right? The source is so close together that you can approximately treat the field as propagating instantaneously. And the correction is coming in from those two vertices, the time derivative. Yeah. So that's how it looks like. And yeah, for convention purposes, let me say that, so this integral is, yeah, so it's E, well, okay, let me write it here. So by this integral, I mean an integral over k, e to the dk divided by 2 pi to the d, right? In the sense that in the end, we want to take the limit of d goes to 3, right? So we still want to work in dimensional regularization, but I mean, no Feynman integral will ever lead to a divergence here, but we still have to introduce d first, so we can get rid of some of the contributions, so to say. So that here at this point, it's useful to go to d dimensions when we look at the Feynman integrals, but we don't need to have the prefactors in d-dimensional form here. Yeah. Yes. Yeah. 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 Okay. And now we have the same for the other propagators. So we have a propagator for A. And again, it basically looks the same like this one, except that we have a minus in front. Then all of this is the same, the delta, the integral. But then we have to multiply it by a delta ij, right? So that's the other propagator. And then for the sigma field, let me visualize it like this. Again, it's the same, but with a plus again. But now from the tensor structure, we have this P, I, J, K, L over here. So that's how the propagators look like. Now, the word line. No, sorry. Now the two vertex. So there will again be 3 of them. But I mean, I'm not going to write down all of them, also because we'll only need the first one in the end. Now the two vertex is often visualized like this. So as I said, it's a kind of unusual vertex, doesn't usually appear in quantum field theory because such contributions you would always include already in the propagator, which you could also do here, right? Then you would get like a plus or like a minus 1 over c square k naught term over here, but we want to expand in 1 over c square, right? So it's kind of a piece of a propagator that's expanded out. And you can do this by writing down explicitly two vertex for it. So this, well, it's, if we just copy what's in the action, it's 1 over 2 c square. However, it's conventional, so to say, to extract a factor of 1 over n factorial for each leg going out of a vertex, right? So that's usually the convention to keep track of the symmetry factors, which means we have to multiply this guy by 2 factorial, 2 coming from the fact that it has two lines, basically. And then, yeah, in the PN world, it's then also quite conventional to just write the term in the metric as the vertex itself. So I'll illustrate then later how this is useful for assembling the Feynman diagram. So here, yeah, basically we just take the term as it appears there. So I think over there it's with a minus, right? So we have taken one of the time derivatives on the other side to the other field, so we can write it as d phi square. So we have the plus here and this additional factor of 2 factorial. And this will be similar for the other two fields. Now, the point particle action. Yeah, so here we have 2 time derivatives acting on phi. If we take one of the time derivatives going to the other phi, basically we pick up the plus sign. Yeah, yeah. Good. So now, as 1 pp point particle, well, it was defined as c square. So it's m1, the mass, times c square, times an integral over the proper time. Now, here, everywhere, basically, we have the coordinate time appearing. So what we need to do is write this in terms of the coordinate time. And what we get then is this factor here, right? And here, we just can plug in our formula for the line element, right? So we take the square root of that guy divided by dt, and that we have to plug in there. And you see there are a lot of 1 over c squares appearing, so we have to expand all that out. One can do this most conveniently with Mathematica also, right? I mean, it's a bit of a not so interesting task to do it by hand. Anyway, if one does it, one gets to the following thing. So it's now an integral over t. There still is the m1 in front of the whole thing. It starts actually with a minus c square. So that's just the energy, the rest mass energy, so to say, but it's a constant, so it doesn't really matter. It's kind of a pre-Newtonian term, if you want. So it blows up in the Newtonian limit when you take c to infinity, but okay. Then you have the kinetic energy, 1/2 v square. So here v1I I define as dxi over dt, the coordinate time. So this is just the Newtonian kinetic energy, no field dependence, nothing. And you get corrections to that, right? So those are kind of special relativistic corrections to the kinetic energy. And this goes on as an infinite series, right? So you have higher and higher powers in 1 over c square. We just go to the first correction now, to 1 over c square. Now those guys, they just remain unchanged in the sense that they don't have any field dependence. You can just take them from here to the final result of the path integral, right? They will just go through because they are independent of the field you are integrating out. But one shouldn't forget to keep them, right? So there's no special Feynman rule for them. They are just, so to say, constant for the purpose of integration, and you just take them to the final result. Now comes the interactions with the fields. So that's the interesting pieces. So there, the first one is just the interaction with the Newtonian potential. So that's the first vertex that we have. And now there are corrections to that. So there's a 3 over 2 c square times phi times v1 square, right? So that looks almost like the Newtonian interaction, but there's another factor of v square over c square going with it. And we also have an interaction at 1 over c with the vector potential, right? So that's quite nice and pleasing to see, because you see, in order to create a gravitomagnetic field, basically you need a moving mass, right? So a flow of mass will create a gravitomagnetic field, just like moving charges will create magnetic fields in electrodynamics, right? So this interpretation with hand wavy works quite well. This is the electric part of the gravitational field, and this A is the magnetic part of the gravitational field. Good. So those are basically all the one vertices, if you want. So the vertices with one outgoing graviton, either phi or an A. Now, next thing that we have is the 2 vertex, which we also had seen in the topologies, which is quadratic in phi. The term quadratic in A would contribute only at higher orders, so we can neglect it here. So this gives a 2 vertex. And yeah, I mean, you may wonder, okay, where's the coupling to the sigma field? Well, this would also give a 1 vertex, and I'm going to write it down, but it will actually not contribute again. And I'll explain why in a second. So the first coupling to sigma looks like this. So it couples to two velocities and gives a factor of 1 over c square. So naively, one might think, okay, it contributes to 1 pn. The problem is you have to connect that graviton with another word line, right? So the only diagram that you can write down is this one. So you cannot have this vertex only once in the diagram. You always have to have it twice, and then it's 1 over c to the power 4. So this guy also doesn't contribute in the end, right? So does not contribute, right? Because the only diagram would be this one that you can write down. Okay. So with that, we are almost there. Now the Feynman rules, the common way to write them in this PN literature is the following way. So just like for the two vertex, we basically just copy the exact form of the action for the vertices. So we are not doing any Fourier transform, etc. yet. Yeah, that's because otherwise, I mean, we would anyway pick up some weird factors of E to the I, K, etc. because those fields are always evaluated at the world line. So one can never fully get rid of the positions in the picture. So we are just going to do the most simple thing and just say the Feynman rule is just the corresponding term in the action, which means for this vertex where we have world line 1 and 1 phi graviton going out, we will just copy the terms linear and phi, which are these two here, right? So these give us the Feynman rule at this order. So we have this conventional prefactor, we have the mass 1, and then we have an integral over T1. So I am now going to attach labels also for the time, because if we have two of those vertices, we need to keep track of the individual time integrals, right? So that's why I'm going to write an index on the time, indicating which time integration it is. And the field, now one has to remember it depends on the location of the world line, evaluated at the given time. And the field itself also may depend explicitly on the coordinate time. So that is important to remember. And then, so to say, we have the 1 coming basically from here. And then we have a PN correction, 3/2 B1 square divided by C square. And also the velocity V, since it depends on the world line, depends on the time. Okay, now next one. So this is the coupling here to the A field. Looks very similar. And again, here we have to, it's better to write down very explicitly which pieces depend on the time in the time integral, because we're going to have several of those later on. So that's how the other vertex looks like. And finally, we have the two vertex on the world line. Now here, again, since we have two outgoing graviton lines, we add this conventional factor of 2 factorial, which, so to say, is kind of compensated by the symmetry factors, if they are taken into account properly. And yeah, so this is coming from this term over here. So it's 2 pi g divided by c square times m1 integral over dt1 by evaluated at the position x1 of T1 and explicitly again on at T1 and the whole thing squared. So those are the Feynman rules. And now from there, from the propagators, the two vertex and those vertices, we can now assemble the diagrams and translate them into Feynman integrals. Yep. So let's start with the very simple one. So we want all diagrams up to 1 PN order, which would be order e to the minus 2, and also at most up to power gravitational constant g to the power 2. And now the approach is, so to say, that we take the topologies that we've worked out before, and we try to see if we can replace each of the gravitons in the topologies either by this one, or this one. And then once we've done so, we can work out now explicitly the power in 1 over c that each diagram will have, right? So that's the logic here. For instance, for this very simple diagram, the one graviton exchange at linear order in G, we already saw that we always need 2 of the word line vertices, and each goes as 1 over c squared. So it's 1 over c to the power 4, and one can drop it. So not many of the combinations will survive in the end. However, one that definitely survives is this one, where we have the exchange of the graviton electric field. Not surprisingly, this should give us the Newtonian potential, right? So let's see if that works out. Now, what we have to do is basically we take the rules that are there, so one for each vertex. And the first thing that we do is we kind of contract the fields appearing in the vertices according to how we draw the lines, roughly speaking, right? So let me just start maybe. So we have now 2 integrals over time because we have 2 copies of this vertex here, right? So we have 2 time integrals, and then we have 2 times those factors here, but evaluated on different world lines at different times. And of course, we also need to keep the prefactor, right? But that's basically how we assemble the corresponding integral for this. We take the rule for the vertex and just write it, smash it together into a single expression, kind of. Now, so the prefactor square would be 4 pi g. So that takes care of the prefactor. Then we have an M1. We have this factor of 1 plus 3/2 V1 square divided by C square, evaluated at T1. And we have another of this factor like this. Right. And now we have the fields. And so for the fields, we also write them down, but we kind of replace them by the propagator, like this. Right. So it seems a bit cumbersome to always keep track of the times, but you will see there are some diagrams where later on where it really matters. So that's what we get. So we basically have two copies of this Feynman diagram. And the fact that we connect those phi's with the propagator basically means we plug in the propagator here, right? So that's basically how to translate the diagrams into the integrals. And yeah, now basically you would have to plug in the rule for the propagator from over there. One thing that one immediately sees is one gets a delta T1 minus T2, right? So the second time integral immediately goes away. The times are equal. So maybe for this one, we wouldn't have needed to keep track of the times, but that is not always the case, in particular, or only, in fact, when you have time derivatives acting on the field. Then you first have to look at the time derivatives, get rid of them until you just have deltas left, right? So here, typically, you have time derivatives acting on the deltas from the propagators. You need to get rid of them first, and then basically all times, again, will be equal, and you will be always left with a single time integral, right? But it's important to keep track of the time derivatives in the calculation. Right, but yeah, otherwise, now we can insert the propagator, calculate the result, and this will be also part of the tutorial in the afternoon. So I'm not going to do this explicitly here, but I can give you the result, which indeed, I mean, it's a Newtonian potential. But we already have some relativistic corrections from these 1 over c squared terms over here. Like this. Yep. And here, this R of t is basically it's x1 minus x2 absolute value. Yeah. So this is basically the Newtonian potential that will come out. Okay. Now, yeah, let me briefly go through some other examples. So it's a bit easier to do the exercise in the tutorial session. Now, the other diagram might be this one, where, well, it's the same topology, but we, as a propagator, we plug in the gravitomagnetic field. And as I said, the third one would be this one, but we can drop. But this actually contributes because this guy goes as 1 over c, right? So if you have 2 of those vertices, it's 1 over c squared, and it's exactly at the right order. But this goes basically in the same way. You have to write down the vertices twice with 2 time integrals and replace the 2 fields that are appearing then by the propagator. And it's even a bit easier because you don't have those additional corrections here, right? But otherwise, it goes exactly the same way. Now, let me give you one example where keeping track of the time derivatives actually matters, namely when you have this vertex appearing. So another example would be you have 2 word lines and you have basically, again, the one graviton exchange, but now in the middle, you have the graviton 2 vertex with the 2 time derivatives. Now, what you have to do then is basically plugging in the two Feynman rules for each of this vertex, but also the one for the field vertex. Yeah? So you get an integral dt1, dt2 from the two wordline vertices. But now you also have the integral d3x from the two vertex and another dt also from the two vertex here, right? Then you need to take care of all the prefactors. So from here you have a 1 over 2 c square, and from the wordline vertex from the two you have another prefactor. Overall, this is 4 pi g divided by c square, and times m1 times m2 from the wordline Feynman rules. Now, basically, we have to construct the fields properly, right? So we have one graviton going out of the wordline and then into the two vertex. So what we would do then is write this as a correlation function or propagator between the wordline vertex and one of those fields, right? Because we are connecting the wordline to the two vertex. So that means now here comes dt of phi evaluated at x t. Yeah. So the diagram and the way the lines are connected to the vertices tells you basically which field is connected to which other field, right? So here, that is to say, you don't put the other word line, because that would mean you are connecting this vertex with this vertex. But that's not what happens, right? We connect this vertex with the two vertex. And then we have the other contraction, basically connecting this wordline vertex with the field vertex. And that goes in the same way. Let's be evaluated at x2, t2, comma t2 d phi of xt. And then here again, you have to insert the rule for the propagators and do the calculation, so to say. But you already see now you get a derivative of the delta function between the times, right? All right. And last one, basically, is the following, where we have this. Yeah. So the diagram with the three vertex, it drops out. I already mentioned that. So the only remaining topology that we have to take care of is this one. And now here also we have to replace each of the propagator by the phi, the a, and the sigma. Now the only one that contributes is actually the one with the phi. If you replace one of the propagators by an a or by a sigma, it's going to higher orders in 1 over c. So this is the only other diagram that one has to compute. So it's not a lot, as you see. Now, here, we have to take care of the symmetry factor. So to say, because we are connecting this vertex twice to the same world line, so it has a symmetry, and the symmetry factor is 1 over 2. So this may look a little stupid because we have first multiplied this vertex by a 2 factorial, and now we are dividing it again by 2, but this is a normal convention that people use, right? So alternatively, what you could also do is you don't include the 2 factorial here, but then you have to work out all the contractions and count them that you can do, right? So that's another possibility. And so to say here, there's only one way to do it. So that's why basically you have to cancel the 2 factorial again. But yeah, I mean, that's how it is. Now we have, again, 3 integrals because we have 3 wordline vertices. So we have a dt1, dt2, dt3, right? We have to include all the prefactors from the wordline rules, which would give a 4 pi g to the square divided by c square. Then we have a factor m1 from the vertex below, and we have 2 vertices on the second word line. So this gives an m2 square, right? And then again, we have to construct the pi fields properly. So one of the fields from word line 1 to the second word line, and then the same again. So this gives this, where am I here? So the first term is quite easy. That's this. However, now the second one has to be a little careful. So we again have word line 1 as the first term, field evaluated at word line 1, and the other field evaluated at word line 2, but it's another word vertex. It's an independent vertex, so it's evaluated at time 3, right? So that's why we need to keep track of the times properly in general. So that's basically how it goes. And then, yeah, one has to plug in the formulas for the propagators, which I gave you, and then do the integrals. And this will then lead you to the first post-Newtonian correction to the Lagrangian or the action. Now, just to conclude this discussion, let me give you some remarks. So there is another diagram because here we always need to flip things. We have to flip word line 1 and word line 2. So one shouldn't forget to include also this diagram, but you don't need to do any extra calculation for that, right? Because you can just compute this result and then you exchange word lines 1 and 2 in the final result, and it's done. But this guy also will contribute. Now, we had a few other topologies, right? So we had also this guy and this guy. This one, and also this one here, right? Now, it is actually not so difficult to see that those guys will always lead to so-called scale-less integrals. Which is to say, in the propagator, you have this integral over k in Fourier domain. Scaleless means that the integrals don't depend on any external variable. They only depend on k. And in dimensional regularization, those contributions are 0, right? So they can be dropped. So that's one nice feature of dimensional regularization, in that those self-interactions are kind of zero naturally. You don't have to do any cutoff scheme, renormalization of the masses, etc. They are just zero in that regularization scheme. But this, so to say, this you could also check during the tutorial, maybe for one of the examples, and then it is kind of easy to see how it follows for the others, right? But then, yeah, once you have all those diagrams and all those, check that all those are zero, you can sum everything up and get the 1pn effective action. And more precisely, you get the effective action where the orbital scale O is integrated out, right? So we have done the next step in the integrating out procedure. First step was to get rid of the body scale gravitational fields. This we didn't do with a calculation, but we more made an intuitive ansatz and said, okay, it's point masses with some corrections. At the next step now, we were integrating out the orbit scale gravitational field. And this we could do perturbatively using the path integral. And it corresponds to basically writing down all the connected diagrams at the given order. And then you translate them into Feynman integrals, you do the calculation, and you get to the effective action with the orbital scale integrated out. Yeah, so that's, so to say, the end of today's lecture. And I hope you enjoyed the tutorial in the afternoon. Thank you.
Do we have a few questions? Any burning questions, or we break for coffee and maybe talk to Jan over the. Okay, so let's try to come back by 11:30.